Now on to part 2 of chapter 2, where we're going to start talking about time, velocity, and speed. Now we have this very precise definition of a second. The unit, the second, had an older definition that wasn't precise and it was hard to repeat. And this is one of the things when we define units, it's very important that I be able to give you a description of the unit that lets you recreate that unit, that standard. So here is what a second is defined as. It is 9,192,631,770 oscillations of a cesium atom. It's a very precise definition. You can set up the experiment in a physics lab. You can do it over and over again and recreate what the second is. So, one of the things with time is usually we're measuring change in time because there is no zero time, right? And so whenever we start a problem, we often, just for convenience, we define the start of the problem as time t equal to 0 and we go from there. That keeps us from having to track, let's say we started this problem at 5 in the afternoon. All right, we don't have to keep subtracting out 5 in the afternoon to get how long it's been. So we just call that time 0. Velocity is movement over time, right? Velocity is movement over time. This is what your speedometer tells you. Your speedometer tells you your speed. Velocity also has in it a vector. So velocity also has direction. Speed does not have direction. Your speedometer reads the same 30 kilometers per hour whether you're heading east or west. It doesn't care what direction you're heading, but your velocity is 30 kilometers per hour east or 30 kilometers per hour west. Your velocity has direction, speed does not. And when we're calculating velocity, the simplest is I've gone from point x1 to point x2 between times t1 and time t2. So this is my change in x divided by my change in time that I experienced. So let's look at an example. Suppose I start off at a position x1 equals a meter at a time t1 equals 1 second, end up at x2 equals 5 meters at t2 equals 3 seconds. Then my average velocity is just 5 meters minus 1 divided by 3 seconds minus 1 is 4 meters divided by 2 seconds is 2 meters per second. Now if I want to give it make sure I know it's a vector, I put the plus 2 meters per second. Right? We can run another example going from minus 3 meters to minus 4 meters over 14 seconds. And that gives me minus a half a meter per second. All right, so the speed in the first one is 2 meters per second. The speed in the second one is half a meter per second. The plus and minus signs give you direction. When we change our velocity, that is called acceleration. Acceleration is just a change in velocity, and it's just like we measure change in position over time is velocity, change in velocity over time is acceleration. So these two, this one looks very much like this one, right? So acceleration is also a vector. And acceleration is a vector because velocity is a vector. So acceleration has a direction. You can be accelerating in the same direction you're going, which what happens when you drive away from a stop sign. You can be accelerating opposite the direction you're going, which is what happens when you come up to a stop sign and come to a stop. If we look at examples, right? Moving 10 meters per second, and 50 seconds later you're moving 20 meters per second, then 10 meters per second over 50 seconds is the difference there. So our acceleration is 0.2 meters per second squared. So here, make sure you pay attention to the units for acceleration. Meters per second squared. Units for velocity, meters per second. Units for acceleration, meters per second squared. Units for position, meters. So here are 3 different curves, all right, 3 different plots. The top one, this is position versus time. This one is velocity versus time. And this last one is acceleration versus time. All right, so let's look at what this means in terms of math, because remember, physics is all about applying math to what we know. Now, if you're at constant velocity, your position is given by where you started plus the velocity you're moving at times time. But if you're accelerating, that's no longer the case. Why? Because, as you can see here, if you're accelerating, if you have acceleration that's not zero, your velocity is changing. You're only constant velocity when this velocity versus time is flat, right up here. All right, so there's acceleration. That leads to this velocity changing. There's no acceleration. That means that's flat. There's deceleration or negative acceleration, or acceleration opposite the direction of motion in this case, and that gives you a decrease in velocity. The effect over here on position is that while you're accelerating, you begin spreading out further, and the distance between these points is growing. You've got constant, then you've got constant acceleration, so it's linear right here, and then you slow down and it's no longer linear. So under constant acceleration, velocity, your velocity at any time under constant acceleration is the acceleration of a period of time, acceleration times time plus whatever your initial velocity was. Your position is 1/2 acceleration times time squared plus your initial velocity times time plus your initial position. At any point, your average velocity is v plus v naught. V naught is your initial velocity over 2, right? And then this last equation, the result of fiddling with these a bit, v squared equals v naught squared plus 2a undo x minus x naught. Now here's the important thing about using these equations, right? We have this set of equations here, right? If we say, hey, we're going to go with acceleration is 0, what do we get? We get that equation, right? Because that term disappears right there. That term disappears right there. And we're down to this equation up here is what's describing what's going on. Another important point. Whenever we have a problem like this, where there's acceleration, there's no acceleration, and then there's acceleration, we have to divide it up into pieces. So we have to look here and say, okay, so we start off with an initial velocity here of 0. All right, so we start using these equations. That's 0. Our initial position is 0, so that's 0. All right, we want to know where we are at any given time. We just take, oh, that's 0, right? 1/2 at squared is all we're left with. 1/2 at squared. What's our velocity? At. So this describes our velocity right here, that line, at. This describes 1/2, up to there, 1/2 at squared. All right, so now we get to this point in time right here, right, where the acceleration is going to change. Well, you know what we have to do? We have to start over, right? We solved the first part of the problem. We solved the first part of the problem by doing the equations, using the equations for this little bit of time, using the equations for this bit of time, using the equations for this bit of time. Now, we have to essentially define a new starting point. All right? Define a new starting point. And now we're going to deal with the next chunk of time by itself. All right? This we're going to treat like a separate problem. Now, what's our initial velocity? Well, our initial velocity for the second part of the problem is wherever the velocity was at the end of the first part of the problem. All right? So our initial velocity for part 2 is our final velocity in part 1. Then we're going to run the problem through all of this, and we're going to get to a point here, right? Here's our final position in part 2, our final velocity in part 2. Now we have new conditions again. Why? Because the acceleration is again different. And so what do? We're looking at a different part of the problem. We've got this little bit up there, we've got this little bit, that part there, we got that, right? So for this part of the problem, our initial velocity is the final velocity at the end of the second part of the problem. Our initial position for the part 3 of the problem is our final position up here at the end of the second part of the problem. So we simply chain the parts of the problem together, right, and treat it like three separate problems. All right, so if we put in a time t equal t1 equal t0, I mean, if we put back in t0, we take t to t minus t0, then you can see what it does to the equations. This is why we most often simply say, hey, for any part of the problem, we're going to start off with that segment of the problem where we're just going to call it 0, right? That's all we're going to do. We're just going to call that time 0. All right, so problem solving techniques. They're pretty straightforward if you've been doing this for a long time. But you're new at this, so you're going to have to go through and figure out how to use these and apply these in each and every situation. There's a lot to learn here. There's a lot to figure out in how to approach problems. There's a lot in terms of making sure you write down, hey, this is what I know. Now, sometimes what you know is not explicit. Sometimes it's implicit, like the starting time for a problem. Or if I say I start from rest, I'm not saying I start with V0 equals 0. Right? I'm not giving that explicitly, but I'm giving it to you implicitly. I start from rest. So there are a lot of things when you look at a problem, you're going to have to sort out what's implicit, what's explicit, what do I know, what do I want to know, what equations are involved that link these two sets of facts together, right? And do I have to find out sometimes, this is a very important thing, sometimes you have to find a third quantity using what you know in order to get to what you want to know. All right, that's it for part 2, and we'll start back with part 3 shortly.